Welcome viewers to the seventh lecture for the online series of lectures for the course of Algebraic Topology 1. In this lecture, we'll be studying simplicial homology groups. As the name suggests, we'll be computing homology groups for a given simplicial complex. Okay, so homology groups. First, we need the notion of orientation. Orientation of a simplex. Okay. So here is the definition of orientation. Let sigma be a simplex define two orderings of its vertex set to be equivalent if they differ by an even permutation. They differ from each other by an even permutation. Okay. So if you apply an even permutation on one ordering, you will get the other ordering. Then you'll say that these two orderings are equivalent. If dimension of this simplex is positive, the orderings of the vertices can then be classified in two possible ways. So which means that there are two equivalence classes. Equivalence classes. Each of the classes is called an orientation of the given simplex sigma. Each of the two classes is called an orientation of sigma. So if sigma is just a zero simplex, then there is only one class and hence only one orientation of sigma exists in such a case. If sigma is a zero simplex, there is only one class and hence only one orientation exists in such a case? So what do we mean by an oriented simplex? An oriented simplex is a simplex with a prescribed orientation on it, with a prescribed orientation on it. Okay, so this is the notion of an oriented simplex. So about the notations, if the points v0, v1 all the way up to vp are geometrically independent, we shall use the symbol v0 dot 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 all the way up to vt without commas in between. Okay, without comma. To denote the simplex. These p plus 1 geometrically independent points span okay. So this is the notation for just the simplex. Okay, and we use the symbol v0, v1, v2 all the way up to vp within square bracket. Okay, so we put the points, geometrically independent points, inside the square bracket with commas in between to denote the oriented simplex. The oriented simplex consisting of the plane simplex v0, v1 all the way up to vp with the given ordering v0, v1 all the way up to vp. Okay, so this is the ordering. v1 comes after v0, v2 comes after v1 all the way up to vp. vp comes at last. Okay, so let me give you an example to illustrate these notions. Example 1, we attach an arrow to a given one simplex, okay, to prescribe an orientation. Okay. So the oriented simplex, the oriented one simplex V0 to V1 is pictured below. Pictured below with the arrow directed from V0 to V1. Okay, so here are the two vertices V0 and V1. We draw an arrow from V0 to V1. So this arrow is going to represent the oriented one simplex V0 V1. Okay. An orientation of a two simplex can be depicted by a circular arrow. Can be depicted by a circular arrow. Okay, so the circular arrow can be either clockwise or counterclockwise. Okay, so there are two possible orientations. So let me draw a picture for that. Say we have three vertices V0, V1 and V2. We form a triangle out of these three vertices. Okay, so when we can either put a counterclockwise circular arrow, or we can put a clockwise circular arrow to prescribe an orientation on this two simplex. Okay, so for example, we can have a picture like this. Okay, V0, V1, V2, something like this. Okay, it is the picture of an oriented one simplex, right? Because the no circular arrow is present here. It just means that it's the union of these three oriented one simplices. Okay, but the triangle is missing here because this region is missing here because we have not put any circular arrow in the picture. Okay, so whenever we have to include the triangle, we have to put the circular arrows. Okay, good. Now see that so look at this picture. Okay, so let me erase. There are too many triangles here. Just skip one of them. So V0, V1 and V2. Okay, and we have a two simplex with a prescribed orientation. Say we have a clockwise orientation. Okay, and so this simplex, this two simplex, is denoted by V0, V2, V1. Okay, this same simplex can be denoted by, say, V2, V1, V0. okay, or V1, V0, V2. Okay, they are all equivalent. They represent the same two simplex. Okay, um, it's easy to check that any two of these three simplices, three two simplices differ from each other by an even permutation. So how do you get here from here? So first you interchange V1 and V0 to reach V1, V2, V0, right? Okay. And then again you permute V2 and V1 to have V2, V1, V0, right? And that way you reach here. Okay. So it's an even permutation. Okay. All right. So since one can be achieved from the other by an even number of permutations, they are all equivalent. Okay. They represent the same two simplex. Now let us draw the picture of an oriented three simplex. So geometrically it means that geometrically it pictures a tetrahedron. So say V0, V1, V2 and V3 are the vertices, okay, spanning the tetrahedron. Okay, I put this face by a dotted line. Okay, so this is the picture of a three simplex or a tetrahedron. We denoted by, so we put an orientation here, V0, V1, V2. Okay, sorry, V0, V1, V2 and V3. Okay, so the orientation does prescribe. So okay, so we can put an orientation this way by a spiral arrow. It means that it's the orientation thus prescribed obeys the right hand screw rule, meaning that if you curl up your fingers, except for the thumb, from V0 to V1 to V2, the fingers of your right hand, okay, from V0 to V1 to V2, then the thumb will be directed in the direction of V3. So this it is said that this orientation obeys right hand screw rule. Right hand screw rule. Okay. So whenever we have a spiral arrow directing this way, directing up, we have this right hand screw rule. Okay. So well, um, we can similarly have the same three simplex given by this notation V0, V0, V2, V3, V1. So it means if I curl up my fingers from V0 to V2 to V3, that phase, Okay, so if I curl up my finger from V0 to V2 to V3, my so if the right hand fingers are curled up from V0 to V2 to V3, the thumb will be directed in the direction of V1. So it means that so the right hand rule applies, and this actually denotes the same oriented 3 simplex. Okay, so this is the notation for the right hand screw rule. Okay, okay, okay. Now consider the oriented 3 simplex V0, V2, V1, V3, which differs from the previous one, from the previous orientate 3 simplex V0, V1, V2, V3, right, by a single permutation. By a single, since a single permutation is an odd permutation, an odd permutation. Okay, so you exchange V1 and V2 here to obtain this oriented 3 simplex. So it means that this guy, this oriented 3 simplex, is oppositely oriented. So this is the picture V0, the same picture. So again, I'm missing it. I should be draw this face by a dotted line. V0, V1, V2, V3. Okay. So so whenever I'm drawing, so I'm denoting this 3 simplex by V0, V2, V1, V3. Okay, and it the orientation is given by a spiral arrow directed downwards. Okay, okay, so this is the other orientation that one can have on an on a 3 simplex. Okay, so now we are in a state to give a definition, give the definition of chains on a simplicial complex. Here is the definition. Let K be a simplicial complex a p-chain on the simplicial complex K is a function C from the set of all oriented p-simplices of the simplicial complex K to the set of integers such that C of sigma is equal to minus C of sigma prime, okay, where sigma and sigma prime are oppositely oriented same simplex, okay. So sigma and sigma prime represent the same simplex with opposite orientation. Represent the same simplex with opposite orientation. Okay, then first of all, C of sigma has to be the negative of C of sigma prime. 2. C of sigma is equal to 0 for all but finitely many oriented p-simplices sigma of K. All but finitely many oriented p-simplices sigma of K. All right. So it which means that C sigma is non-zero only for finitely many simplices of K. Elsewhere, C of sigma is 0. Okay, so we can add two such p chains. Say if we have a p chain C, another p chain C prime, then we can add them up, okay, to obtain a new p chain. So this new p chain C plus C prime is defined in the following way: C plus C prime acting on a p simplex of K, on an oriented p simplex of K, is defined as C of sigma plus C prime of sigma. Okay, it's just pointwise addition. Okay, where sigma is an oriented p simplex of K. P simplex of K. All right. So with this pointwise addition of p chains, the set of all p chains form a group. Right? Because we have the additive inverse coming from this point 1. Okay, so it forms an abelian group. So we will call this the group of oriented p chains of K, and denoted by Cp of K. Okay. So there are two extreme situations. If P is so I think I need to stop the application and reopen it. So where were we? Let me reopen the sketchbook to resolve the problem. If P is less than 0 or P is greater than dimension of K. So K is the simplicial complex that we started with, which has a given dimension, determined by the dimension of the largest simplicial complex, the largest simplex it consists of. Okay, if P is larger than the dimension of the simplicial complex, or if P is less than 0, in both cases we let Cp of K denote the trivial group. The trivial group means it consists of only the identity element. Okay, the group consisting of the identity element only. Okay, good. If sigma is an oriented simplex, the elementary chain C corresponding to sigma is the function defined as follows. Okay, so associated with each oriented P simplex we can obtain an elementary chain, okay, the value of which on that particular oriented P simplex will be 1 only. Okay, and on the same simplex which is oppositely oriented, the chain is going to give the value -1, elsewhere it's 0. Okay, C of sigma is equal to 1, C of sigma prime is equal to -1, where sigma prime is the same simplex as sigma with opposite orientation. Okay, C of tau is equal to 0 for all other simplices, for all other oriented simplices tau. Oriented simplices tau. Okay, All right. Now, a word of confession. We'll be engaged in the following abuse of notation. It's important to note that we'll be engaged in the following abuse of notation. We'll use sigma to denote not only a simplex or an oriented simplex, but we will also denote the elementary P chain C by the same symbol sigma, by the same symbol sigma corresponding to the oriented simplex sigma. Okay, all right. So it's important to have it in mind that we'll be engaged in this abuse of notation. Okay, so in this notation we write sigma prime is equal to minus sigma, where sigma prime is the same simplex with opposite orientation. Okay, so instead of writing C of sigma prime to be equal to minus C of sigma, we just write sigma prime to be equal to minus sigma. Okay, all right. So now the first lemma of this lecture, Cp of k, all right, the group of oriented p chains on the simplicial complex K is free abelian. A basis for Cp of k can be obtained by orienting each p simplex of k, okay, and using the corresponding elementary chains as a basis, and using the corresponding elementary chains as a basis. Okay, so the proof is quite straightforward. First, you orient the p simplices of k arbitrarily. Okay, each p chain of k then can be uniquely written as a finite linear combination. So C is a p chain, and that can be written uniquely as this finite sum ni sigma I, which we number by 1. So there are finitely many terms in this sum. Okay, okay. So this is a finite linear combination of elementary p chains sigma I. Okay, so these are uh, uh, elementary p chains corresponding to the oriented p simplices of K. First of all, you put orientation to all the p simplices of K arbitrarily. Once you have all the p simplices of K to be oriented, then you can write any p chain of C as this finite linear combination of the elementary p chains. That is going to be any p chain. Okay? The chain C, for example, here, C, since C is a function on the oriented p simplices, so what value does C take on a given on this oriented p simplex sigma I? Okay, so the value chain C takes on the oriented p simplex sigma I is just the integer ni. Okay, and the same simplex C takes the value minus I on the oriented p simplex sigma I with opposite orientation. All right, and takes the value 0 on all oriented p simplices not appearing in the summation. Since it's a finite sum, there may be some oriented p simplices missing in this finite sum, and on those simplices the value of this p chain C on those simplices are 0. Okay, all right, so we are done with the proof. Now note that the free abelian group, so we are talking about this free abelian group of p chains on the simplicial complex K. So p can be 0. So the free abelian group C0 of K has a natural basis. By natural basis, we mean that it does not depend on our choice because it's equipped with a natural choice. There is one possible orientation because we are just dealing with zero simplices, and on zero simplices you cannot put orientation. So there is one possible way you can orient them, which means that there is one choice we are left with. So that is the reason C0K is said to have a natural basis. As for zero simplices, there is only one orientation, only one one can ascribe. Okay, so otherwise, so if CPK for P greater than 0, this free abelian group does not have a natural basis. It depends on our choice of orientations we put on the P simplices of this simplicial complex K. Okay, does not have a natural basis. Okay, okay, now an important corollary to lemma 1. We have seen in lemma 1 that Cp of K, the free so the group of oriented P chains on the simplicial complex K is free abelian, and we can take the all the elementary P chains, oriented P chains, to be the basis, of this free abelian group. Okay, so this corollary tells us that any function f, from the oriented P simplices of K to any abelian group, any arbitrary abelian group G, extends uniquely to a group homomorphism from Cp of K, which is a free abelian group, to the abelian group G. Okay, there is a group homomorphism which is unique, provided that this holds f of minus sigma is equal to minus f of sigma, where minus sigma is the oppositely oriented simplex one obtains from the oriented simplex sigma. For all oriented P simplices sigma. So the corollary above is a consequence of lemma 1 together with the universal property of free abelian group. Okay, what is the universal property of free abelian group? So if S is a set, okay, we are given a set S, and let us denote by Z to the S to be the free abelian group, on S. Okay, so we have seen earlier in the previous lecture, in lecture 6, that it is actually the set of all functions from S to Z. So it consists of functions from S to Z such that phi of small s is equal to 0 as belonging to S for all but finitely many elements of this big S, the set that we started with. Okay, so one can interpret this free abelian group on S as the collection of all such functions phi. We have seen it earlier. Okay. Um, Now, given an abelian group G, given an abelian group G and a map F from S to G, okay, the set that we have, from that set to the group, to the abelian group G, we just have a map. Okay, then there exists given these two things, there exists a unigroup homomorphism, G from Z superscript S to G, with G composed with this hook is equal to F. So in other words, the following diagram commutes. So let me draw this commutative diagram. There is the inclusion of this set S in this free abelian group on S. Okay, that's what we mean by hook. Hook is the inclusion of S in Z to the S, the Z raised to S, which is the free abelian group on S. And there is this given mapping F from S to G. Okay, and there exists a unique group homomorphism G between these groups Z to the S and G. Okay, so this is a commutative diagram. So G composed with I is going to be equal to F. So in the present context, S is the set of all. S is the set of all oriented P simplices of K, of all oriented P simplices of K. Okay. And Z to the S in our case is this CP of K. Okay, is the free abelian group of all P chains, of oriented P chains on K. So now using lemma 1 and this universal property of free abelian group, we immediately see why corollary to lemma 1 is true. Okay, so to describe it a little more, given C is equal to a finite sum, right, Ni sigma I, this guy belonging to CP of K, meaning that it's a P chain, oriented P chain on the simplex K. How can we define this unique group homomorphism from CP of K to the arbitrary abelian group G? How do we define this group homomorphism? So we define G from CP of K to the free abelian, the abelian group G by G of sum over Ni sigma I. This is a finite sum, so finitely many i's are there. And this is going to be equal to sum over all I sum of all these expressions ni times f of sigma I. Okay. We are given this function f. We are given this function f from all oriented P simplices to the abelian group G. Okay. Okay, so now it makes sense. The right hand side makes sense. Okay, f of sigma I, they are all in G, and an integer times a group element means that if it's a positive integer, it means that group element is supposed to be added to itself n many times. So if ni is a positive integer, then ni times that group element means that that group element is going to be added to itself ni many times. And if ni is negative, it means that we take the inverse of that group element, which is minus g, and we are supposed to to add minus g to itself ni many times. Okay, so this way we can interpret these terms being in the abelian group G. Okay. Okay. So this is what I have written down here. Let me erase it and write it. Recall, if X is in G with G abelian, then minus X is also in G, right? Which is the inverse of the group element G. Group element X. Also, nx is equal to x plus all the way up to x. So it's an n-fold sum of x to itself. N-fold sum of x with itself. And minus nx is the n-fold sum of minus x with itself. This is n-fold sum. This is also n-fold sum. Okay, so this was the correlative theorem 1. Now we need the definition of boundary operator. Okay, but before that we take a break. We take a short break and then we'll be back with this definition of boundary operator. Thank you for attending the first segment of this 7th lecture.